Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Nvidia. We have Stephen Jones. He is the Alliance Manager for Deep Learning at the company. Stephen, how are you doing today?
I'm doing great, thanks.
Well, thanks for coming on, Stephen. I understand that the upcoming GPU Technology Conference has a kind of a theme wrapped around deep learning, and I wanted to learn more. So, thanks for coming on. And what can you tell us? What is this all about?
Yeah, certainly. So for our GPU Technology Conference, we have a kind of the theme of the conference is on deep learning. There'll be a number of sessions around deep learning, and we'll have a lot of luminaries in the deep learning and machine learning field actively participating in the conference. So let's talk a little bit more about deep learning. I'll give you a background and hopefully a good understanding of exactly what deep learning is. So Jan LeCun, who is the director of AI research at Facebook, he talks about the unreasonable effectiveness of deep learning. So to really break that down, deep learning itself it's a subset of machine learning, and it refers to artificial neural networks that are composed of many layers. Now, I know that sounds kind of complex, so I'm going to break it down a little bit, kind of tell some stories about it, and then we'll get into a little bit more of the details. But so initially, what does John mean by unreasonably effective? So it turns out that deep learning is just stunningly effective across many problem domains, and it's really transforming the way that computers achieve perceptual tasks today. And by perceptual tasks, I mean things such as pattern recognition, computer vision, speech recognition, and even medical imaging. So I find the best way to communicate this stuff is kind of to tell some stories about it. And to be clear, there's nothing confidential here. These stories that I'm telling, you can Google all of these. They are all available, right in media on the web. Where I'll start is with Facebook's Deep Face. So this is a technology that Facebook has just developed that it actually creates a 3D model of your face from the online photos you post up there. It adjusts your face for different lighting conditions and facial expressions. And then it can actually identify you across photos from different angles, different facial expressions, different lighting environments with about 97% accuracy. And this is all using deep learning. Now, this is significantly better than what competitors can do today, and just slightly, about 1% worse than humans can do in identifying faces. So, while we can all imagine very evil uses for this technology, Facebook actually has an altruistic motive here. They actually plan to alert you that a picture has been posted to Facebook with your image on it, and it gives you the opportunity to blur it out. Say that you're in a situation where you don't want it to be known publicly that you are in, or you're not happy with the results of your photo, whichever. Mm-hmm. Another great story that's in the media today is around the Skype translator. So the Skype translator performs instant translations of text chats in over 40 different languages. But the real killer feature here is real-time spoken translation between English and Spanish. So deep learning lets Microsoft's computers transform the audio speech into text, and then it's translated using standard methods. If you haven't seen the videos online demonstrating this, it's really quite heartwarming. They have some school children, English school children, that are talking to Spanish-speaking school children using this technology, and it's just fascinating to see the kids be able to interact in this manner. Other great stories in the medical field. So deep learning is being used to detect the genes that are associated with autism spectrum disorder and helping people with autism. It's being used to detect and suppress the various brainwave patterns that are responsible for epileptic seizures. So you can see that in some cases we've talked about images We've also talked about audio and speech. In this case, for epileptic seizures, we're talking about signal processing of the data that's returned from the brain. Other great stuff. Deep learning is being used to identify skin cancers, to classify the sounds in your lung for specific diseases. It's being used to computationally design drugs, which just saves millions of dollars in research. So you can see, deep learning, very powerful field, very exciting stuff going on here. And again, this is all right out of the news in the last month or two. So let's talk then about specifically what is deep learning. So the concepts around deep learning have actually been around for some time. Most recently, it arose from artificial neural network research that was conducted in the late 70s, early 80s. It was popularized by researchers such as Jeff Hinton, Jan LeCun, and Yoshua Bengio. Now, deep learning involves training a neural network to learn to identify specific patterns, and it does that using multiple levels of abstraction that you can see represented here. So for an example like images, one of the layers can look for very simple low-level concepts like edges or perhaps contours. Another layer may look for high-level, very complex concepts like maybe an ear or a nose. So initially, the network learns to identify some information in each layer, and it will refine it at that layer and pass it down to the next layer. And while the first layer may learn to identify an edge, the next layer may learn to identify collections of edges that form a particular shape, and so on down the line. Finally, this combined information will allow the computer to identify a face or a car or another object. The fascinating thing about these algorithms is they're not tied to one particular object. They're tied to the data on which they're trained. So if they're trained for faces, they learn to identify faces. But if they're trained for cars, they'll learn to identify cars. Before deep learning, there were these handcrafted feature detectors. So engineers would sit down and they'd come up with a specific algorithm that could identify an eye or a nose or a wheel. What we've learned from deep learning is that given sufficiently large data sets that we see today, thanks to social media and that type of thing, computers are actually better at engineering these features than people are. So again, these multiple layers of transformations going from, say, pixels to edges to textures really closely resembles how the brain structures, and this is where the term deep learning comes from. So let's talk about why GPUs are really good for deep learning. So the popularity of deep learning today really stems from the availability of computer processing capabilities, high performance computing, the availability of large amounts of data for training, be it images or sound or MRIs or whatever is out there, and then just general advances in machine learning algorithms and research. So one of the best examples of this unreasonably effective nature of deep learning is the annual ImageNet challenge. So this challenge allows research teams to compete on a variety of image classification tasks using a standardized data set that consists of about 1.2 million training images. And within these images, there's about 1,000 categories of objects that these researchers are trying to identify. This is objects like a cat or a dog or a lamp or a car. Again, historically, people use these handcrafted algorithms to identify this stuff. This was back 2010, 2011, and you can see that there's about, we're getting about 26% error rate in that time frame. So in 2012, a team from the University of Toronto used GPUs to train neural nets, and they blew away the competition. You can see the error rate here in 2012 dropped to about 16%. This is a jump that was never heard of before. So today, actually in the last month, this competition has become really hot. Baidu has come out with a application called Deep Image that claims about a 5.3% error rate here. Closely following that, Microsoft Research came out with an algorithm that claimed 4.9% accuracy, and Google topped that with a 4.8% error rate. So this is a really hot field, lots of interest here. What's really interesting is that the human error rate for identifying things in ImageNet is about 5.1%. So we're actually getting to the point where computers can beat humans in this arena. So achieving these kind of results really requires a huge amount of computational power. For instance, out of UC, there's a deep learning framework called Caffe. It can actually process over 40 million images a day with a single Nvidia Tesla K40. That's about 5 milliseconds per image to train it, and about 2 milliseconds to classify it or identify what's in the image. So you can see the training time here is huge, and the computational power that's required is very significant. One way to really illustrate this is a story about Google's DeepMind and how they've trained deep neural nets to play classic Atari games. One of the best examples that they've shown is the game Breakout, if you'll recall that from the late 70s, early 80s.
Sure.
So after about an hour of training on Breakout, and this was about 200 games, the software actually had about a 30 to 40% success rate. After about 2 hours of training, the software never misses the ball and actually plays better than any human possibly could. After between 4 and 6 hours, suddenly this deep learning software learns how to outsmart the game. And it plays more offensively than defensively, and it's actually strategically trying to win more efficiently. You can actually search YouTube for videos of this, and it's absolutely fascinating to see the software learn to master Breakout. But in the end, GPUs are just surprisingly well suited for deep learning. So these neural networks, especially what's called convolutional neural nets, which is a special type of deep learning layer, these are all inherently parallel algorithms, and GPUs can easily take advantage of this parallelism. Neural networks are usually defined as a matrix, and again, GPUs are just optimized for matrix operations. And then finally, these neural networks just require a huge amount of flops, and exactly what GPUs provide. So GPUs have been shown that they can deliver the accuracy of prediction at least as good, if not significantly better, than other solutions. The reason it's better is because since it's faster, you can train more data, making the network more accurate. But it also provides these results faster. You have a smaller footprint, within a data center, and lower power consumption as well. So moving on, who's using deep learning? Well, there's actually quite a large body of research out there now that are describing the use of GPUs for deep learning. And as mentioned earlier, our GPU technology conference this spring is really going to be focused on deep learning, featuring a deep learning track, industry luminaries, hands-on lab, as well as networking and social events around deep learning. It's really covering both industry and research by storm. Lots of stuff going on. And then lastly, I'd like to mention just kind of some of the GPU-accelerated deep learning frameworks out there. So there are a large number of available open source projects that support deep learning. We're focused on the most popular ones right now, and we continue to kind of reach out to the community and see what's most popular, what's being used. Caffe is a deep learning framework that was developed by UC Berkeley, and it's an active development by the Berkeley Vision and Learning Center, as well as a number of community contributors. This is easily the most popular framework, and it's used heavily for the ImageNet challenge that I mentioned earlier. It's really easy to use, easy to modify. All of their models that they train and develop in the software, they make freely available for download. Anyone can go in, download them, start experimenting, start modifying. And most recently, they've added segmentation and sequencing capabilities. So the interesting thing about this is segmentation allows you to, instead of looking at objects, you can look at parts of objects, identifying a wheel on a car or a leg on a horse, something along those lines. Sequencing really opens up temporal type capabilities. So you can think of analyzing video or something like that, opening the door for video classification, video understanding, identifying where objects occur within YouTube. And this will lead to things like activity recognition and sentiment analysis. Very exciting field, lots of cool stuff going on there. Torch is a scientific computing framework, and it has more of a wide focus on general machine learning algorithms. So this includes deep learning, but also includes other facilities for what you might consider processing of big data, for instance. It's very easy to use, comes out of NYU, and most recently, Torch Consortium was formed really to encourage collaboration on the code, more code sharing, code reuse. This consortium has a number of industry participants, Facebook, Google, and Twitter and Nvidia, just to name a few. Next is Theano, which is a math expression compiler. Makes it really easy to write deep learning models, and it's widely used by academia and in research. And then CUDA CovNet is kind of one of the original deep learning applications written by Alice Kaczynski, who was a key member of the team that introduced deep learning to ImageNet. Two more things I'd like to mention. One is cuDNN. This is NVIDIA's GPU-accelerated library of primitives for deep neural networks. It has been integrated into all of these open source frameworks. The goal of cuDNN is to allow researchers to focus on deep learning research, algorithms, that type of thing, and we focus on writing low-level CUDA code or optimizing for specific GPU architectures. And then finally, a really interesting thing is multi-GPU deep learning training. Currently, most of these frameworks function on one, maybe two GPUs, but as you can see with all of the training data coming in, we need to be able to scale. So all of these frameworks are looking to scale to 4, 8, 16 GPUs in a box, and then scaling larger, multiple nodes, that type of thing, to handle the amount of data that needs to be processed to appropriately train these neural networks. If you have more questions, we have a site that we've put up at developer.nvidia.com/deeplearning, which has lots of references, course information, papers. You can get a much deeper understanding of deep learning. I've just kind of touched the surface here.
Well, great. Well, Stephen, a question that comes to mind right away, seeing this is, why haven't I heard about deep learning prior than, I would say it's been about maybe 18 months is when the term first came to notice here in HPC and big data. Was it just there weren't machines or devices that made it feasible, or what would you say?
No, I mean, that's a great question, and you're exactly right. It has been the last 18 months or so. I think what really brought it to light was that 2012 ImageNet competition. That in 2012 we saw one team using GPUs in deep learning. In 2014, we saw something on the order of 110 teams. In fact, there was one team that did not use deep learning. I think it's taken that long to really just gain momentum for researchers to really get deeper involved and to understand the technology behind it and learn to apply it to different areas.
Yeah. And what would you attribute? I mean, Nvidia has been talking about these kinds of topics for a while at the GTC conference, but to make it a major theme of the conference, what's changed out there? Is it reaching critical mass, would you say?
It really is. We are seeing proposals for all kinds of research in machine learning, and it started just in the image recognition space,
Hmm.
and now it's scaling for all kinds of different things. I see applications for identifying land use characteristics using deep learning. Applications for very specific audio processing and tracking. It's suddenly become just part of the conscious that everyone realizes. Hey, I have a perceptual task that deep learning might be good for.
So, Stephen, where is this all headed? I mean, as far as the next set of developments, are we talking about new algorithms, finer meshes? Where do you think it's going?
I think all of that. There'll be more algorithms. The layers in these networks will continue to grow. The applications in this space are innumerable, from automotive self-driving cars to medical applications. I think once we get over our fear of artificial intelligence ruling mankind, this type of functionality will enrich our lives considerably.
So net, you think it'll grow the demand for GPUs out there and for different kinds of like embedded devices as well as for workstations and servers?
Definitely, it already is.
Uh-huh.
We're certainly seeing applications in the drone space,
Yeah.
in the robotics space. It's embedded stuff is huge. Online stuff is big. I think we'll see this covering most aspects of our lives at some point.
Oh, terrific. Well, Stephen, I want to thank you once again for coming on the show today.
Thanks, Rich. I really enjoyed it.
Yeah, thanks again. All right, folks, that's it for the Rich Report. Stay tuned for more news and information on high performance computing.